welcome to another exciting video from Exam Essentials. This is your favorite tutor, Mukto sir, and today we are basically going to discuss Unit 6 of October 2024. So without further ado, let's get started. The first question, as you can see, number 1 says compounds P and Q are crystalline solids. P is white and contains one cation and one anion. Q is pale violet and contains two cations and one anion. Now, a student carried out tests to identify P and Q. The to complete the table is shown by name or formula of the products of the tests. Now, as you can see, the tests are provided. If we check out the first test right here, it says that aqueous silver nitrate and dilute nitric acid were added to a sample of an aqueous solution of P. Concentrated ammonia solution was then added. The observation was that a yellow precipitate was formed which was insoluble in concentrated ammonia. Now that is enough. First of all, when we add silver nitrate solution, what happened is that a yellow precipitate was produced. Now we know that from our previous knowledge, when yellow precipitate is produced, this only means that there is a presence of silver iodide. If it was white precipitate, then it would have been silver chloride. And if it was the cream precipitate, then it would have been silver bromide, right? So in this case, obviously, it was, we can see the observation was in yellow precipitate, so we can easily say that the precipitate is nothing but silver iodide. Moving on, we saw a sample of solid Q was added to a 5 centimeter cube of aqueous sodium hydroxide. Okay, now if that's the case, then we can see that when it was added, a pungent gas was evolved which turned damp red litmus paper blue. And then we can see that a red-brown precipitate was formed which was insoluble in excess alkali. Now, of course, these two clues are very important. That it says that it's insoluble in excess alkali, and a pungent gas was evolved. Pungent gas, which basically, turned the litmus paper blue, that means that the pungent gas was an alkali gas. And the only alkali gas that has been taught in the A-level course was ammonia. So we can write that the gas was ammonia. On the other hand, they said a red-brown precipitate was formed which was insoluble in excess alkali. We know that the presence of Fe3+, the Fe3+ ions are red-brown, they tend to produce the red-brown color. And on the other hand, since it's insoluble in excess alkali, so we can easily say that the precipitate was nothing but FeOH3 dot H2O3. That is the complex compound of iron 3. This is the complex compound. The reason why the red brown precipitate. This is the red brown precipitate. The reason why, which is the color was shown, and it is insoluble in excess alkali. Moving on, we can see the third one that says the aqueous barium chloride and dilute hydrochloric acid were added to a sample of solution of Q, and we can see a white precipitate was formed. Now we know that this test is basically referred popularly as the test of sulfate ions. So we can easily say that the precipitate produced was barium sulfate, because the barium ions from barium chloride and of course the sulfate ions which is present in the solution of Q, these two react together in order to provide barium sulfate, which is of course the color is white precipitate. Moving on, number 2, a green flame was seen when a flame test was carried out on a sample of solid P. Identify P by name or formula. In the previous test, in the first test to be honest, we basically identified the presence of iodide ions in sample in the solution of P. And now we can see that flame test is basically used for identifying the cation in one sense. So in this case, a green flame was provided, and as you can see very clearly, I have provided a list. We can see that for the presence of barium 2+ ion results to the formation of a green flame color. So we can say that the cation here is Ba2 plus and the anion is iron minus, which provides us the compound, the solid P, is actually nothing but barium iodide. Okay, so this you can either write it in words, or you can either also write just the formula like this. Moving on, let's move on to the next one. They said give the formulae of three ions present in Q and hence the formula of compound Q. Now, what did we see in the tests in compound Q? We saw that in Q a pungent smell was provided, and we also determined the presence of Fe3 plus ions. Moving on, we also saw that there was the presence of sulfate ions as well in Q. So we can say that the three ions, the one cation and two anions that were present, or the ions that were present in Q, were Fe3 plus, we can say NH4 plus, the ammonium ions, and of course the last but not the least, the sulfate ions. So using these ions, we can now formulate the formula of Q, which is nothing but FeNH4 NH4 SO4 2. Okay, because if the question is why did we give 2 right here, because it actually helps to neutralize the charges. That's why I give a 2 right here. This is all about the valency concept, nothing else. Moving on, the student added a sample of a pale brown aqueous solution of Q to a colorless aqueous solution of B. The student observed the formation of a darker brown solution along with a white precipitate. Okay, this is very important, this line right here, along with a white precipitate. Now, the student concluded from the formation of the darker brown solution that a redox reaction had taken place. Explain why the student came to this conclusion. Now, the presence or the production of a darker brown solution basically means that the iodine, which was present in the aqueous solution in the aqueous solution of P, it was basically uh, oxidized to iodine, because only when iodine is produced, the solution basically turns darker brown. So what we can say is that pretty simple. We can say iodide ions have been reduced, sorry, oxidized to iodine. While on the other hand, we can say that since the redox reaction have taken place, so obviously our common sense says the Fe3 plus ions present in the solution of Q must have been reduced, because we know that in a redox reaction both oxidation and reduction takes place. So we can write it down that on the other hand, the Fe3 plus ions get reduced to Fe2 plus ions. Okay, so the formation of a darker brown solution basically indicates that iodine was produced, and from this we can say that the student came to the conclusion that a redox reaction has taken place, since obviously if iodide ions are oxidized, so yeah, the Fe3 plus must have been reduced. Moving on to number 2, we can see in question number 2, a group of students investigated the kinetics of the reaction of peroxide disulfide ions. Some of the iodine produced in reaction 1 may be removed by including a portion of sodium thiosulfate in the reaction mixture. Now the thiosulfate ions react with the iodine, as you can see in shown in reaction 2, and this is the reaction. After all the thiosulfate ions have reacted, any further iodine produced can be detected by the formation of a starch iodine complex. Student M carried out a sequence of experiments to determine the order of reaction with respect to iodide ions. The volumes of the solution used in the mixture are shown in table 1. So you can see the table is provided, and you see the mixture, the volume K2S2O6, and then you have the volume Na2S2O3 and the volume of water which was added or produced. The concentrations of the solutions used are also provided, and the procedure here has been outlined. As you can see very clearly that in step 1, a few drops of starch solution are added to 5 cm cube sodium thiosulfate solution in a small beaker, and in step 2, the potassium peroxide disulfate solution and water are added to the beaker, and then potassium iodide solution is added, and the whole mixture is stirred, and a timer is started. The time taken to change color is recorded, and the procedure is repeated for each mixture using the volumes shown in Table 1. Now, moving on, if I say so, let's start with the questions. Suggest a suitable piece of apparatus for measuring the volume of the potassium iodide solution. Now, in this case, we need to check out in potassium iodide solution right here, which were the solutions which were used. Well, we can suggest many things. We can say, how about a burette? We can basically use a burette, or we can also use a graduated graduated pipette basically means pipette with markings basically. So we can either use any one of the general measuring instrument for measuring the volume of the potassium iodide solution. Moving on, state the final color of the reaction mixture in step 3. Now in step 1, we have already added a few drops of starch solution, so obviously when the titration will take place, when the potassium iodide solution will be added, the iodine is going to react with starch, and the starch iodine complex produced at the iodide ions basically will result in the production of iodine in, as you can see in reaction 1, and any further formation of starch for formation of iodine is going to produce the starch iodine complex. So when the starch iodine complex is produced, the color of that starch iodine complex will be the final color of the reaction mixture in step 3. So we can say that the color is blue black. Moving on, they say the reciprocal of the time taken for the react mixture to change color can be used as an approximate measure of the initial state. Now state why the amount of thiosulfate ions should be much smaller than the amount of peroxy disulfate ions for this approximation to be valid. Now remember, they say 1 by T. This is the time taken for the mixture to change color. So the whole point of thiosulfate ions here is basically it is used in order to remove some of the iodine which is produced in reaction 1 right here. So the excess iodine produced gets removed by the reaction with thiosulfate ions. So if it is it's very crucial that reaction 2 finishes up very fast and before the concentration of the change in the concentration of the main reactants, which is the peroxide disulfate ion and the iodide ions from potassium iodide, can be observed, right? So we can easily say that if we want to if you want the thiosulfate ions if you want the thiosulfate ions to allow the reaction to happen very fast, so we can say uh, to, to complete before reaction 1 shows significant changes in the concentration of its reactants, we would be requiring the thiosulfate ions to be added as in as very low amount as possible. So that is the reason why that we should add the thiosulfate ions in very small amount. So we can say that so that the thiosulfate ions get used up quickly in reaction 2 before the concentration of the main reactants change significantly. So the whole point here is to measure the time taken for the mixture to change color. That means what we are trying to say that we would be requiring to observe the change in concentration of the peroxide disulfide ions and the iodide ions right here. So this is basically like an axis reaction happening, and we would be if it finishes faster, it would be much more better for us, so that we can so it does not hamper our observation when of our the change in when the change in concentration of iodide ions and the peroxide disulfide ions takes place significantly. So this is the reason why we should use the thiosulfide ions in very low amounts, so the reaction 2 goes into completion more faster than reaction 1, or the whole all the thiosulfide ions get used up before reaction 1 starts showing significant changes in its concentration, especially in the concentration of its reactants, which is crucial for for observing or measuring the time taken for the mixture to change color. Okay, so now let's move on to the next one that state why it is important the rate of reaction 2 is much faster than the rate of reaction 1. Exactly my point. Just like in the previous questions answer that I've mentioned, is that the whole point here is what in reaction 2, the whole point here is to ensure that the excess iodine gets removed via reaction 2 by reacting with thiosulfate ions which are added. So this is very important for the reaction 2 to be faster than reaction 1, so that the iodine which is which we want to be removed gets disappeared in the reaction by reacting with the thiosulfate ions before any reaction with the starch can occur. Okay, so because if we are not able to, because we will be wanting to check out the color change or color change when the starch iodine complex is produced, when the iodine produced in reaction 1 reacts with the starch, not with the iodine that we want to be removed in that reacts with sulfate ions in reaction 2. Okay, so it's very important the reaction 2 finishes faster and more finishes faster and at first compared to reaction 1. So we can write it down that so that the iodine disappears in the reaction with thiosulfate before any reaction with the starch can occur. Okay, fine. Let's move on to the next one. They said the results that student M obtained are shown. So these are the results of the reaction, the time taken, the reciprocal of the time taken for the mixture to show the color change, and these are the concentration of iodide ions, the time taken for the color change, basically. So complete table 2 with the iodide ion concentration in mixture 3 using the information from table 1 and the concentration of the potassium iodide solution. So we can see that table 1 has been provided, and now in order to find the concentration of potassium iodide solution, all we need to do is to divide the number of moles with the volume. So in order to the volume that we can see very clearly is that we can see that the total volume here is 11, 20, 5, and 9. So if we add them up, we tend to get about 45 cm3. So that is the total volume of our potassium iodide solution right here. And we can see that the concentration is provided. And of course, the volume, its individual volume is 11. So we can easily find the mole by multiplying 11 with 0.20 right here. And we can get the moles. Okay. So using this formula, using the moles right here, we can just divide it with the total volume which was used in mixture 3, which is about 45 cm3, and we can easily find the concentration right here. So we can write down that concentration of mixture 3 is nothing but 11 times 0.200, which is the number of moles, divided by 45. Eventually we tend to get about, if we use the calculator, we tend to get about 0.049 mole per dm cube. So 0.049 is the correct answer. Next, I said plot a graph of 1 by time against the iodide ion concentration. So if we use the graph, the data provided in the table and plot a graph. This is going to be something like this. The 1 by time, the reciprocal of the time taken for the color change, is going to be in the y-axis, while the concentration, the iodide concentration, is going to be in the x-axis. And if you plot the points provided from the table provided right here, we will be able to get a graph something like this, which is what? A straight line actually passing through the origin, with one of the point actually slightly in the left side, but not, intersecting the main line, to be honest. But still, this is the graph when you plot from the table, from the graph, from the table provided. Moving on, if you check out, deduce the order of the reaction with respect to iodide ions. Now, since the graph we can see after plotting is a straight line passing through the origin, we can easily say that the reaction is about first order with respect to iodine ions, because we can see clearly that since the graph is a straight line passing through the origin, we can see that the rate against concentration here is basically what? A straight line. That means the rate here is directly proportional to the concentration of iodide ions, right? So we can say that the reaction is first order with respect to iodide ions, since the graph of rate against concentration of I minus ions is a straight line passing through the origin, which means there is a positive correlation between the concentration of I minus ions and its rate of reaction. So the reaction is first order with respect to iodide ions, and that is how, by seeing the graph, we can justify our reasoning and answer. Student N carried out a sequence of experiments to find the order of the reaction with respect to peroxy disulfide ions using solutions with the same concentration. Now, the volumes of the potassium peroxide disulfide solution used were different. State two other variables which should be kept the same. Now, the two controlled variables we can say is that we should keep the temperature for each of the experiment while carried out same, because temperature greatly affects the reaction rate. So if the temperature remains same for each and every solutions of peroxide disulfide ions each time the experiment is carried out, the experiment will remain fair. Another variable that's going to keep the fair, going to maintain the fairness of the experiment, is the total volume of the reaction mixture. So if the total volume of the reaction mixture is kept the same, then we'll be able to get a valid reaction rate for each of when each of the experiment is carried out. So we can say that since the volume of the total volume, to be exact, and what I mean by total volume is that no matter what volumes you take, right here as you can see in table 1, no matter what volumes you take, total volume of each and every reaction mixture must be kept same. That is what I'm trying to say. So the total volume of the reaction mixture must be kept same. Now, student N found the reaction is first order with respect to peroxide disulfide ions. Now, since we already know the reaction is first order with respect to iodide ions as well, so we can easily write the overall rate equation, which is about rate is equal to we tend to know that the exponents of the concentration of the ion tends to reflect the order with respect to that particular reaction. So in this case, since peroxyl sulfate is first order, so we can just easily write as S2O8 2 minus 1. And also we found that iodide ions is also in first order with respect to this reaction, so that is also 1 as well. So overall, when we add these two exponents, we tend to get that the overall rate order for this reaction is 2. It is about second order, which is about second order. So this is the overall rate equation for the reaction with peroxidized sulfate ions and iodide ions. Moving on, we can see that student R carried out experiments to find the activation energy of this reaction. So similar procedure was used to determine the rate of reaction at two different temperatures. So these are the values provided. They're told to calculate without drawing a graph the activation energy of this reaction. Now, in order to calculate this, what we can do is that we can create two simultaneous equation with the provided data in the table. So the first the simultaneous equation would be by using this equation we can see that ln k, right? So we can our the ln k value is provided, which is about negative 6.03 is equal to negative EA divided by R, which is about 8.31. So we can just easily write as 8.31 times, of course, we can see 1 by t. Right, now we know that 1 by t is provided in the first value, it is about 0.00351, and that is our first part, plus we are able to have a constant right here. So this is our first equation, and the second equation would be if you had negative 3.47 is equal to negative EA, again 8.31, times, if we use this one right here, 0.00314 plus constant. So now we know in a simultaneous equation we have EA, one variable, and constant, another variable. So we can now simultaneously solve in order to get the EA value from here. And if we do that, then what happens is that if we do that, like if we subtract equation 1, if we try to do that, so if we subtract equation 1 from equation 2, we are able to get about something like negative 2.56, which is equal to negative EA. I'm here subtracting equation 1, equation 2 from equation 1. So if I basically subtract the left side, I tend to get negative 2.56, and again if I subtract the right side, I tend to get about, if you subtract this right here, so I tend to get about 0.00037 divided by R. And when we do subtract this, since both constants are similar in both of the cases, so we can just omit them out. Now we have this equation right here, and now we can now make EA the subject just by cutting the signs in both sides. So we will be getting 2.56 R divided by 0.00037. So eventually the value that you get, it is about negative 6918.9 Kelvin, basically negative 6.91.8 Kelvin, which if you multi this is for this part, the value is negative 6918.9, and if you then multiply it with R 8.31, the final answer that you tend to get is about 57.57496 per joule per mole, basically, to be honest. And then if you want to convert it into kilojoules, so you can just divide it by 1000 and you tend to get about 47.450 kilojoule per mole. So that is the value of EA, and the sign here is obviously plus. Well, why is it plus? Well, that is because the reaction is an endothermic reaction. Right here we can see that, and we can see that the temperature is increased. Moving on, if we part of the question paper, which is number 3. You can see that ethane dioic acid in solution is an acidic bridge fluoride. They have said a fact about ethane dioic acid, and the student determined the value of X in a sample of ethane dioic acid by titration with pressure manganate 6 solution. 7 to be exact, not 6. So this is the reaction, and the procedure has been outlined right here, where in step 1 we can see that a sample of 1.27 gram of solid acid is dissolved in deionized water to make 250 cm of solution. Now describe how to make 250 cm of solution of ethane dioic acid in step 1. Now this is the process of dilution, and in the process of dilution what we do is that at first we tend to add distilled, or in other words deionized water. Distilled water basically means water with no ions, so this add distilled water to the solid 1.27 gram right here, obviously in a beaker. So now after you add distilled water to the solid in a beaker, you transfer the solution. Basically by adding distilled water, you tend to the solid in the beaker, you tend to dissolve the solid and create a solution. To create a solution, then you transfer this solution to a volumetric flask with the washings. What do we mean by washing is that in the volumetric in the beaker right here, when the solution is transferred to a volumetric flask in something like this, we tend to see that some of the water, or some of the solutions droplets tend to stay in the body, in the interior body to be exact, of the beaker. So we have to basically take out this as washings and then transfer this as well into the volumetric flask, so we tend to get, so that we can, so that we will be able to get a more accurate value when we measure the volume in the volumetric flask. And after that what we do is that the third step, that is that you make up to the mark with deionized, or in other words distilled water, and invert to mix. And then invert to mix the solution effectively. So basically after you transfer the solution, you then basically again repeat step 2, and then add water till 250 cm cube is reached. So basically in the volumetric flask we'll be able to calculate that measure that number by checking the markings in the body of the flask. Moving on, the next part is that explain why in step 2 the ethene dioic acid solution was measured using a volumetric pipette, but the dilute sulfuric acid was measured using a 25 cm cube or measuring cylinder. Now, in most cases, it's pretty simple. We can say that the volume measured, the first case is pretty simple, that is that volumetric pipettes are much more accurate in tend to provide a much more precise measuring values compared to measuring cylinder, which tend to have a higher percentage uncertainty. So we can easily say that volume measured using a measuring cylinder is less accurate than a volumetric pipette. And on the other hand, the reason why the ethane dioic acid was basically used was basically for in the case of ethane acid, the volumetric pipette was used for measuring it, was that in this case you can very clearly see that this one, the H plus ions which come out from the sulfuric acid is in excess amount, and the limiting factor here is due to the stoichiometric equation is 5:16. You can see the limiting factor is ethane acid. So it is very highly important that the limiting factor or the reactant which is less in amount, it should be measured more accurately compared to the compared to the reactant which is in excess amount, because at one point the ethane acid is going to, the concentration of the ethane acid is going to change fast, and it's going to end up pretty, at first compared to the sulfuric acid, which is going to stay in excess amount at the end of the reaction. So we can easily write that the amount of ethane acid here, because the amount of ethane acid here acts as a limiting factor. Or you can also say in the reverse argument that the sulfuric acid is in excess amount, so that is kind of very, it makes it very less important to accurately measure the the excess reactant, which is sulfuric acid in this case. So moving on, state why the titration needed no indicator. Well, first of all, what we can see very clearly that KMnO4 was added, and KMnO4 has its own color. So during the titration, at the end point of the titration, the KMnO4 will basically turn pale pink at the end points. That will act as a self indicator itself for the whole titration. So we can easily say at the end point, the MnO4 minus ions act as a self indicator, turning pale pink. Okay, now suggest why in step 2 the temperature of the mixture at the start should be 60 degrees, but not further warming is needed after a smaller quantity of potassium manganate 7 solution has been added. At the start it should be 60-degree, and the only logical reason is that the reaction, obviously, now we know that for reactions which have high activation energy, more heat energy is required. So in this case, higher temperature will be required. So that is the sole reason why at the start of the reaction, if we can provide higher temperatures, the activation energy will be met and the reaction can be initiated or ignited. So we can say that the reaction has a high activation energy at room temperature, which is about 25 degrees Celsius, right? So we can, if we can just increase the temperature, in this case they mentioned 60, we'll be able to meet up the required activation energy and allow the reaction to ignite. So as a result, the reaction will be faster at a higher temperature, such as 60 degrees Celsius. Now, they again said that no further warming is needed after a small quantity of the potassium manganate 6 solution has been added. Why is that the case? Because we can see very clearly in this reaction that Mn2 plus ions are produced as one of the products, which acts as a self-catalyst. So when you tend to add MnO4 minus ion, what happens is that the product is produced. So the concentration of Mn2 plus ion is increasing. So if the amount increases, this will result, for this will basically increase the mechanism of the catalyst, or the strength or the effectiveness of the catalyst, and hence, in other words, increase the rate of the reaction at a lower activation energy, because we know that catalyst basically uses an alternative route with a lower activation energy in order to increase the rate of a reaction. So we can write it down that the Mn2 plus ions, we can write it down that the Mn2 plus ions, the Mn2 plus ions produced in the titration reaction acts as a catalyst as the reaction progresses. The sole reason why lower activation energy is required and the reaction rate increases automatically. Moving on, they said the mean titer was 19.90 cm cube. Determine the value of X in COOH dot XH2O. The first, since the titer has been provided, we can easily find the moles of the manganese-6 ions that have reacted in this titer. So we can write that the mole of manganese 7 right here, since the volume has been provided, and since the volume has been provided, we can see clearly right here. We can easily, what we can do is that we can easily just divide it with, when easily divided with 1000 and convert it into TM cube right here, and then multiply the concentration of potassium manganate 6 solution, which is about, we can see clearly above right here, 0.0203. So we can just write it down right here, that is about 0.0203, and you will be able to get the value, which is about 4.0937 times 10 to the power minus 4 mole. So that is the moles of the manganese ions. The next thing that we'll be requiring is that we'll be requiring the moles of the ethane dioic acid in 250 cm cube. So in order to do that, what we need to do is that we need to, because now we know that the moles of manganese 6, it's now pretty simple to find the moles of the ethane dioic solution. So the next thing what we can do is that we need to check out the stoichiometric equation right here. So in the stoichiometric equation, you can clearly see that the ratio is about 5:2. We can see the ratio is 5:2. The 5:2 ratio of ethane dioic acid ions and the MnO4 minus ions. So we can easily use the ratio and find the moles of ethane dioic acid, C2O4 ions. So we can write the moles right here of manganese provided, which we have calculated right here in the previous step, multiplied by the mole ratio, which is about 5 by 2 times 10. Now, why I give 10? The reason why I gave 10 is that since they basically in the first step, you can see very clearly that 250 cm cube of solution was, basically was produced by dissolving deionized water. And how is it possible? It is only possible if you are able to add 25 cm cube of ethane dioic acid solution 10 times of it, right? So if you make it 10 times, you'll be able to get the 250 cm cube solution of ethane dioic acid, which we have created down here. Moving on, if we do that, so if you multiply by 10, so we'll be able to get the value, which is about 1.0099 3 times 10 to the power minus 2 mole. So this is the mole of C2O4 minus. The next thing that we're going to do is that now we find the mass of water in the solid, because after you can find the mass of water in solid, we'll be able to find the mole ratio of ethane dioic acid and water, which we can use in order to find the value of X. So for finding the mass of water in solid, what we can do is that we should be able to omit, if we can omit the mass of the solid, if we can omit the mass right here, we can see very clearly that we know the moles of 1.0093 minus 2. So if you can omit the mass of ethane dioic acid from the solid which we have added in the solution, we'll be able to get the mass of water. So if we do that, what we can do, we can easily basically write down as 1.27 minus the this one right here. If we just 0093 times 10 minus 2, if we multiply with the molar mass of ethane dioic acid C2O4, which is about 90, we tend to basically get it is about 0.36107 gram. So now we know the mass of water, and we also tend to basically know about the moles of ethane dioic acid as well right here. So using the mole ratio, so if you use this mole ratio right here, so COOH 2 is to the mole ratio water right here. So if you use the mole ratio, uh, we know the moles of ethane dioic acid is about this much, which is 0 point, if you write it in decimal point, is about 0.101 is to if you basically find the moles of water, you can find the moles of water right here. If you can just divide the mass provided, which you have found, with the molar mass 18, so you'll be able to get about 0.020059, about 0.020059. So you can just write 0.002059. So that is the moles of water. And now if you find the simplest ratio, so you will get it is about 1:2. So the value of x right here is 2. X is going to be 2, because when you find the mole ratio, so the mole ratio here is that we can see that the mole it kind of actually matches, and it kind of actually makes sense. We can see that 1:2. So the mole of ethane dioic acid here is 1, while the x value, or in other words the moles of water here, is 2. Moving on to the next one question, they said ethane dioic acid dissociate in 2 steps. The first dissociation equation has been provided, as you can see, and they also provided the acid dissociation constant, which is about 5.6 times 10 to the power minus 2, and the corresponding pKa, which is about 1.25. They told to outline a practical method that would enable us to confirm the value for this first acid dissociation constant, and the indicator data has been provided. Now we know that a diprotic acid basically tend to have first equivalence point and second equivalence point, since as they've already mentioned that there are 2 dissociation steps, how a diprotic acid basically dissociates. So a practical option is to basically use the equimolar solutions of ethane dioic acid and sodium hydroxide and perform a titration. So in titration, what do we do is that the first step is that we can write that we tend to add small portions of sodium hydroxide, and obviously while adding small portions of sodium hydroxide, we will note the pH of the solution, or of the mixture you can say, after each addition. So this will basically help us to draw a graphs of something like this. So after you note down the pHs, obviously using mixture of, after each addition using a pH meter, obviously you should use a pH meter because it will be able to provide you a much more accurate reading of the pH. The second thing that you're going to do is that you're going to perform the first step, and perform the first step until the first equivalence point, or in the other word, the first neutralization uh, point has been reached. So we can just write until the first equivalence or neutralization, actually better would be neutralization, until the first neutralization point is reached. So how will you understand a neutralization point is reached? By noticing a sharp rise in pH, or you can say that you can easily determine using the color change of any of the indicators down here, except for phenolphthalein, because obviously that color because obviously you can say that the pH, it does not, the pKa value which has been provided, as you can see, 1.25, it actually does not fall within phenolphthalein, right? So we can write down that what for until the fuzz is reached by checking the color change of an indicator, of a suitable indicator to be precise. And the last thing that you're going to do is that you plot a graph of pH against the volume of alkali added, and you can then determine the half neutralization point. So this is the practical method in how you can basically, obtain the value for the first acid dissociation constant, because using the half neutralization point, the pH at the, half neutralization point, we'll be able to calculate the pK, pKa value, and then using this pKa value, we'll be able to get the acid dissociation constant. So this is the practical method that has been outlined down here. Moving on, the next part in number 4, the question is about azo dyes, which is used to dye cotton fabric. So the azo dye 1, phenyl azo 2 naphthanyl. Naphthol can be made from phenylamine by reacting with sodium nitrite and hydrochloric acid. So the reaction here is provided, and you can see in very clearly the benzene diazonium ion then undergoes this further coupling reaction with 2 naphthol and producing an 2-phenylazo 2 naphthol and azo dye right here. Now, phenylamine used in reaction 1 is labeled with the following hazard symbols. Now, they told you to state the meaning of each symbol. Now, this hazard symbol basically means that when you add something up, or when any of the chemical falls on your hand, it poses a huge danger to your skin. So we can say that the reaction 1 is corrosive. The sign of a skull basically indicates that the reactants involved in reaction 1 or the products involved in reaction 1 are indeed poisonous or fatal. Okay, or fatal. On the other hand, in this case, basically this means that this type of sign with a human body and a white star sign basically means that the products or the reactants are going to cause serious or long-term health hazard if exposed, with prolonged time. So we can say that serious long-term health health hazardous. Moving on to the next part, they said practical instructions for the preparation of 1-phenylazo2-naphthol are shown. In step 1, the phenylamine dissolved in hydrochloric acid in a beaker, which is placed in an ice bath, and then the temperature is between 0 degree and 5 degrees Celsius. A cooled aqueous solution of sodium nitrate is added drop by drop. A solution of 2-naphthol dissolved in aqueous sodium hydroxide in a boiling tube, and then it was placed in an ice bath. And then in step 4, the mixture from step 3 was then added very slowly to the solution from step 2 containing the diazonium salt. Now the small red crystals of the product were formed over several minutes. And in step 5, what happened is the crystals were filtered off under reduced pressure using a Buchner funnel, and then washed and recrystallized with ethanoic acid. And we can very clearly see that a data book of the data book melting temperature of 2-phenylacetate was 131 degrees Celsius is stated. Explain why the temperature for reaction 1 must be kept between 0 degrees Celsius and 5 degrees Celsius. Well, the common sense says that we can say that below 0 degrees Celsius the reaction is pretty too slow, and above 5 degrees Celsius the diazonium salt, which has been produced in reaction one, right here you can say this diazonium salt is basically, or the product, the benzene diazonium ion, this is basically going to decompose, because we know that each we know that what we know that it is actually kind of unstable. So if the reaction is too, if the temperature is too high, then it's going to decompose and produce something else, which is about phenol. So we can write that below 0 degrees Celsius the reaction is too slow, while above 5 degrees Celsius the product of reaction 1 will decompose and produce phenol instead, which we don't want, because if phenol is produced, then the whole point of this reaction becomes a failure, and produce phenol instead. Okay, nextly, draw label diagram of the apparatus used to filter off the crystals under reduced pressure in step 5. Now, as I said, we tend to basically use a Buchner funnel, and a Buchner funnel simply looks something like this. A conical flask is drawn right here, and in this conical flask, this is basically called a Buchner funnel, this right here. And in this, in the above part, knob is provided, right, something like this, and inside the knob, in between the knob, we are connected with, of course, a Buchner funnel right here, something like this. And this pipe right here, this one basically is connected to a vacuum pump, and this conical flask is now known as Buchner flask. Buchner flask. So the vacuum pump is basically used in order to suck all the air out from the Buchner flask, allowing the constituents or the reaction products to filter off the crystals under high pressure. So, and in the Buchner funnel, we tend to have a specialized filter paper which allows the crystals to fall down. So we can, oh no, which basically allows the solution to fall down where the crystals stay above the filter paper. So this is the filter paper. We can just label it off something like this, and that is the Buchner funnel right here. And we can also say that these small holes right here in the filter panel, this basically acts as an integral platform for the solution to fall through the funnel to the flask, while the crystals remain above the filter paper. Okay, so this is basically a live example of the apparatus used to filter out the crystals under reduced pressure in step 5 of this whole procedure. Moving on, they said outline how the melting temperature of the crystals may be measured to ensure that an accurate value is obtained. So now after we filter out the crystals, what we can do is pretty simple, is that you place a sample of the solid crystals in a capillary tube. So after you place them in a capillary tube, then you insert this tube into with a teal tube with a thermometer. So insert the capillary tube. The capillary tube is also known as a teal tube. So because the scientist Thiel basically invented it, that's why the capillary tube was also, is also popularly known as Thiel tube. So we can insert the capillary tube or the Thiel tube in a water, oil bath to be exact, in a water bath with a thermometer in order to measure the melting temperature, of course. Then what we do is that you heat the water bath to 110 degrees Celsius. Why 110 degrees Celsius? Because you can clearly see that the melting temperature of the crystal was about 131 degrees Celsius. So we will try to we'll try to basically provide as much more heat as possible so that the temperature reaches something above 100 degrees Celsius, in this case about 110 degrees Celsius. And then we will decrease the amount of heat so that the, you know, solid tends to melt slowly until 131 degrees Celsius reach, where the whole solid completely melts. Heat the water about till 100 degrees Celsius, then slowly allow the sample to melt. Okay, so this is how you can basically measure an accurate value of the melting temperature using the thermometer as this process goes on. Okay, moving on, they said azo dyes were developed during the 19th century, but workers in the industry showed high rates of bladder cancer, and the production of some dyes was discontinued. So the introduction of a sulfonic acid group into the dye used for black ink for inkjet printers has significantly reduced the toxic effects. The formula for a sulfonic acid side group is shown. So this is the sulfonic acid group. Suggests how the change in solubility caused by the introduction of the sulfonic acid group reduces the toxic effects of the dye right here. So first of all, as you can very much clearly see that uh, this is we can see very clearly that SO3, the sulfonic acid, is negatively charged. So I mean, it's charged, to be honest. So that basically means that this is going to be a polar compound, right? So this is going to be a polar substance. So the polar substance is basically going to get, going to get attracted, or it's going to be surrounded by water molecules more easily. In this case, you can say the water molecules are going to basically, encircle the polar compound, because we know that like uh, like versus like, you know basically means that solubility is available. Basically, that we are trying to say is that since it's a polar compound, and we also know that water is also a polar solvent, so the solute right here is going to get dissolved in water. Now, what's the benefit? So if this basically, gets dissolved in water more easily due to its polar nature, so what's going to happen is that the dye, which is used for blank ink for inkjet printers, this is basically going to get removed from our, it's going to basically get removed more faster from the body. So if it gets removed from the body or our hand, so what will happen is that this will be able to help the, workers in the industry to experience the toxic effects in a reduced manner. Okay, so we can just write it down, is that the solubility in water of the dyes increases due to the polar nature of sulfonic acid group. So the dye is lost from the body more easily, or washed off more easily. So if it's washed off more easily or removed from the body more easily, so the workers will be able to experience reduced toxic effects, which will, at the long term is going to, which will in long term is going to be healthier for their body. So that's with this question, we're done with Unit 6. So that's it for today. Basically, we'll be back with another paper solving video another time. Till then, like, share, and subscribe, Exam Essentials, and goodbye.